All right, so today we're going to finish the multiple linear regression. We're pretty much close to the end of it. Okay, we covered most of the topics that I wanted you to know in linear regression, but we have a couple of more. So reminder, here's what we did in the previous class, and this script, by the way, is posted out there. I believe I updated that yesterday on Scholar. So we're still predicting the Corolla, Toyota Corolla prices, and for that last class, we performed the procedure called backwards stepwise elimination, right? Stepwise backwards regression. So what we did is we said, okay, let's include all the predictors, right? So price tilde dot in our LM function, okay? And then after that we said, well, by looking at the output, at the summary of the model, we can see that not all the predictors are contributing, right? And we started to remove them, starting from the p-value, from the highest p-value, right? The most useless variable. As long as it exceeds our threshold, which we chose to be like 0.5, right? Standard 0.05, 5% significance level. Then we removed engine volume. We removed the color, metallic versus non-metallic, automatic versus manual, and number of doors, okay? So let me go ahead and run this. I'm going to run all these lines, and here is the summary, okay? And in the summary, all the remaining variables I can see are statistically significant, right? Because all of p-values are very low. I see E minus 0.06, minus 16, so really low p-values, right? And I can see that also by the stars. 3 stars mean it's strong evidence to support that the variable is significant and it should stay in the model, right? So this is our simple, fairly simple model. Okay, so another thing that I'm going to do is, remember when we did the simple linear regression, we said price only depends on the mileage and nothing else. We said every time we have to look at the residuals, right? The errors. And the errors should be, first of all, the residual plot should look like a uniform cloud with average 0, right? And we should have half points above 0, half points below 0, right? Some residuals are positive, some are negative, so sometimes I'm over-predicting the price, sometimes I'm under-predicting the price, but on average, I'm right on the money. So average error is 0. That's one thing. Another thing is residual plot should have no patterns, right? It should be a uniform cloud of random points with the same thickness everywhere, and there should be no trends, curves, no patterns at all, right? And that includes the thickness, right? If we see that it has like conical shape, residuals are getting smaller or larger, right? That's something that we call heteroscedasticity, right? And that's also a bad sign. And then another thing that we looked at was distribution of the residuals, right? A good model should have residuals to be normally distributed. So let's check all of these things with my current model, okay? So I believe in the past, actually, I promised to tell you, maybe I did show you, how to calculate residuals. There are 2 ways, right? I can predict the values using my model and then calculate the difference actual minus the prediction, that's residuals. Or I can use the function resid. Okay, so let's do it both ways actually. So calculate residuals. So first thing, I'm going to calculate predictions, right? So my prices, predicted prices. How about that? Predicted underscore prices. Okay. And I'm going to use the function predict, right? Predict using the model Corolla multiple regression model, okay? And my data, well, I'm going to call it new data. It's the same as old data, and that is Corolla underscore data, okay? So I'm predicting prices, which I already have in the file, right? I'm just using it through my model. Throw in predictors, and that means what? Age, mileage, fuel type, weight of the car, so whatever is left in the model, right? And just calculate what should be the price according to my linear model, okay? So I'm going to run this line. and it should give you no red, right? Everything blue. That means that I calculate residual predictions. It's not residuals, it's predictions, right? And now my residuals is function hold on. That's a different way, right? This is an easy way. So I'm taking my predicted prices and subtracting the actual, right? Predicted minus actual, or other way around, actual minus predicted. Let's do actual minus predicted. Corolla data price, that's the actual value for each car, right? Minus predicted prices, that's what my model tells me. Okay? And it will calculate 1,000 numbers, right? Because there are 1,000 cars in the data set. Simple as that, okay? So let's take a look at the plot, for example, okay? So scatterplot, that is, right? I'm going to say plot residuals versus, let's say, mileage, okay? So I believe the first one that I have to specify for the plot function, the first variable is x, right? And that's what it tells me. See that? The tooltip, this is called tooltip, right? The dynamic help, okay? Tooltip tells me that the first one should be x. So let's say mileage, okay? So from Corolla data, I'm going to pick mileage. And that's my x. And the y is a bunch of residuals, right? So y is residuals themselves. Then. Okay, so when I run this line, this is my residuals plot. Okay. Does it look okay to you? Well, first of all, does it look like the average is 0? Average error is 0. Yeah, pretty much, right? It's center of cloud. Do you see any curves, patterns, anything? No, not as much, right? And the thickness, I mean, you can argue that, yes, there is some heteroscedasticity going on, right? Because here residuals are kind of more different than over here. But this is barely noticeable effect, right? So overall, I think it's a well-behaved plot, okay? All right, so let me comment here, residual plot. Residual plot. Let me now go ahead and do another plot. I'm just going to, remember, programmer should be lazy, right? Copy-paste is your friend. So I'm going to do another plot, but now instead of versus mileage, I'm going to plot it versus age. Can I do that? Yeah. So it's the same residuals, they're just going to be shuffled a little bit, right? Because now horizontally I have age. Okay, so I'm going to run this line. And this is what it looks like versus age. So what do you think? Is it well behaved enough? I mean, if you have a certain degree of imagination, you can say, yeah, there is a curvature going on a little bit, right? Could be, okay? But it's not very big, okay? So this is not too bad. All right, and just for fun, let me do another one where I'm plotting residuals versus, I believe the horsepower is left in the model. We didn't eliminate that. Yeah, horsepower. Horsepower. Okay? And I'm plotting the residuals versus numerical predictors, right? I'm not going to plot that against fuel type, because fuel type is categorical predictor, okay? So let's run it against horsepower. Yeah, it's a little bit weird plot, right? We have like these bands of points, right? But that's just basically a reflection of the fact that horsepower is not just a random number, right? There are fixed values for the variable horsepower. How big is the engine, right? So they can't just take any value. So this is not too bad also, right? Average is 0, and mostly I don't see any shape. So that's good. Okay, so now let's see distribution of residuals, okay? So I'm going to plot the residuals distribution. And again, what I'm looking for really is normality, right? Residuals should be normally distributed around what value? 0, right? The average error should be 0. So therefore it should look like a bell-shaped curve with average of 0, more or less, okay? How do I plot the distribution of numerical variable? What do we call the distribution of numerical variable? Starts with age. Histogram, right? So residuals is just a bunch of numbers, right? And I want to plot distribution of a bunch of numbers. How do I plot histogram in R? Hist, yep, hist. And all really I need to do is say what I want to plot, the name of my variable, right? And that would be residuals. I want to plot the residuals, that's it, okay? So it's very simple. So I'm going to run this line, and there it is. Does it look like the average error is 0? Yeah. Does it look like it's bell-shaped? Yeah. It's PDG actually. Pretty darn good, right? So I'd say my residuals are well behaved, right? I didn't see any criminal behavior in residual plots, right? No lines, curves, strands, nothing. Then distribution of errors is normal. That's good. But there is one more test that we need to conduct. And this one is kind of important, okay? This is called multicollinearity. Did you discuss multicollinearity in BUSN 231? No? Okay. Here goes. Before we get to see if the variables have multicollinearity, let's discuss independent versus dependent variables. Now, true or false, ladies and gentlemen? In my model, I have independent variables or predictors. Some of them are numerical, and one of them I believe is still categorical, right? I believe I eliminated the color metallic, non-metallic, and transmission type automatic versus manual. Fuel type is still in the model, right? But I have age, I have mileage, and I have horsepower, I believe, still in the model, okay? True or false? We call these predictors, the other name for them is independent variables. And my price is dependent. It depends on age, mileage, and all the rest of them, right? Now, here's the conundrum though, ladies and gents, okay? What if my predictors are not truly independent from each other? Here's what I mean. Isn't that true that as the car gets older, the age goes up? It also gets more mileage on it, so the mileage goes up. So there might be actually a good correlation, right? The older the car gets, the more mileage we accumulate on the car. So therefore, age and mileage may not be independent from each other, right? And that's something that we need to check. How do we do that? Remember, last week or so, we discussed coefficient of correlation, right? And we said that there are three kind of gradations, right? How strongly two things are cross-correlated with each other. We said that if your coefficient of correlation is between -3 and +3, so it's close to 0, how do we call that correlation? No, between -0.3 and +0.3. Weak, right? It's close to 0. So if the coefficient of correlation is close to 0, we call it weak. And then if it's between 0.3 and 0.7 or -0.3 and -0.7, we called it moderate. And if above 0.7 or lower than -0.7, close to plus or -1, then we called it strong, right? Okay, so here's what I'm going to do now. I will adopt the very same mindset, and I'm going to say, if my two predictors, okay, are strongly correlated with each other, that means that they're either close to +1 or -1 on the coefficient of correlation, then I'm not going to call them independent, because that essentially means that if I change one, it pushes another one, right? They kind of go together, right? Either there is a positive relationship between them, which is strong, or negative relationship, which is also strong, right? And therefore, if that is the case, if the coefficients of correlation between two predictors are really high, more than +0.7 or less than -0.7, then I'm going to say that, hey, they're not independent. They're practically telling you the same story, okay? Because they're hooked up with each other very strongly. One moves, it basically causes the other one to move as well, okay? And therefore, I don't really call them independent. And if that is the case, this is the condition that's called, ladies and gentlemen, multicollinearity. So let me write it down. Multicollinearity. Ooh, what is that? Let me scroll. We call that, okay, multicollinearity. Okay, this is situation when some numerical, that concerns only numerical predictors, okay, disclaimer, because coefficient of correlation can be calculated when your x and another x, x1 and x2, both numerical. When some numerical predictors, let me call it xi and xj, are strongly correlated. And what does that mean? That means that the coefficient of correlation between them, so I'm going to call it R, coefficient of correlation between xi and xj, the absolute value is between 0.7 and 1, right? That's what it means. Okay? That's what it means. So, I'm going to have to take a look at at all really predictors, okay, and take a look at which ones are highly, strongly correlated with each other. And if I find that any of my predictors are strongly correlated, that's actually a red flag. That does not mean, that doesn't kill us necessarily, okay, but that can result in some really weird results in my model, okay, and hopefully today we'll have some time for me to show you what can that be, okay. So this is bad, okay, if we're kind of dumbing it down to good and bad. Multicollinearity is bad condition, okay. Ideally, all your predictors should be either moderately or weakly correlated with each other, okay. That's excluding the target. Hopefully my predictors are strongly correlated with target. That's what I want. But among themselves, predictors should be weakly correlated or moderately at most, but not strongly, okay? How do we check for that, right? Okay, so ladies and gents, allow me to introduce you to another fairly powerful model called GG-ALI, okay? So how do we call the library GG-ALI? We need to install it first, right? So remember how do we install things? We didn't install things in a while. Let's do it. Install packages, right? That's how we did it. So here I'm going to say quote unquote, and it's capital G. GG, both caps, LI, or LI, GG-LI, LI. Okay, like this. Install packages, GG-LI. And you, of course, can do it through packages, right? We did it both ways. You can go through packages, click install, and here just type GG-LI, and then click install button, same thing, right? So I'm just going to go to do it through code. So when you hit enter, well, it says updated. Okay, so update. I installed it basically. It will take some time probably, right? Yeah, so there is a bunch of libraries that are being downloaded. It will take probably, is it installing on your machine? Okay. Okay, cool. Now when installation is done, are you done? Did it come to an end? Okay, cool. Now what do I need to do? What's the next step? Library, right? I installed it, now I have to load it in the memory. So I have to say library GG-ALI. Bam. Okay. Now I'm loading this library, and there it is. Okay. And now what I'm going to do is plot all pairs of correlation. So here's how it's done. Okay, so I'm going to let me put a comment here. Plot a matrix, variable matrix. Okay, variable plot matrix, scatterplot matrix. Scatterplot matrix. Okay, so here's how it's done. So let me show you first simple form without much of the parameters, and then I'm going to be choosing picky about which columns I pick. Okay, so all I have to do is just say GG pairs. Okay, and you should see this function as you type. Since you loaded the GG-ALI library already, right? So you just type GG pairs. Okay, And all I have to do is tell what data to use, okay? And my data is called Corolla data, right? Just like that. I say, plot me all the pairs. That's what it means essentially, okay? So in your data set you have columns, right? There's price, mileage, age, etc., etc. So what I'm saying is take all possible pairs. Price, mileage, age, mileage, horsepower, all of them, right? And plot them against each other. Okay, so I'm just going to do that. And I believe it will, yeah, it will calculate all kinds of burritos for me. It will take some time. And when it's done, it takes some time, right? Do you see the same red stuff? Good. And when it's done, then over here in the plot area, I should see this. Do you see the same? No? Yes? GG pairs, Corolla data. So this is what you should get. Okay? Yeah, it'll take some time to generate. It's not the quickest thing in the world, but at the end of the day you will see the matrix of pairs of the variables. Okay? So let's take a look at how to read this thing. Okay? Well, first of all, it's a little bit excessive, right? I have a bunch of variables. So I don't know if you realize it or not, but I plotted every single variable in my data set against every single other variable, right? So vertically here, or horizontally, I have price, age, mileage, fuel type, horsepower. So all columns. And vertically right here, I have the same listing, right? Price, age, mileage, etc., etc. Okay? So it just plots everything. Okay? So let me make it smaller. Okay? Let me just go ahead and limit that only to the columns that I have selected to be my predictors, right? And what did I select to be my predictors? Oh God, help me remember that. So here's what I'm going to do. I'm going to say columns, right? I'm going to say don't plot me all variables. Not all the variables that you can find, but columns are equal to C. What's the function does? Tell me. Combines, right? It combines things, right? I'm going to explicitly tell which columns I want. I want to say combine the following names, right? Let's keep the price, just for the heck of it. Price, okay? Then I say comma. The next one is, I believe, age is one of my predictors, right? Then after that I have mileage. I believe I didn't eliminate mileage. Still one of my predictors. Oh God, what else? Let's see. Age, mileage, type of fuel, horsepower, and weight. Okay, cool. So here I'm going to say horsepower. And also weight. So I'm kind of telling the function GG pairs to plot only these variables against these list of variables, right? So I don't want to see what we eliminated. Number of doors, metallic, non-metallic color, automatic versus manual, all that I'm basically saying, yeah. They're not in the model anymore, so there is no need, right? And I'm going to run this one again. It will take some time, and it will update for me the list, right? So my list is not very huge, okay? All right, so let's see how to interpret this thing. Well, first of all, there is an upper triangle, and there is lower triangle, okay? And there is diagonal, okay? Did everybody get this thing? No, why not? Okay, so it's coming, right? After what? Horsepower, weight. The last one is weight. So that's basically all the variables that I have in the model right now, right? Everything else I eliminated because the p-values were high, right? I didn't want them for the p-values reason, right? Okay? How are we doing? Yay? Okay. So let's take a look at the diagonals, okay? On the diagonal, this one, for example, it's the price, right? I'm looking at the column, it's called price, and I'm looking at the row, it's price, right? So it's the price against the price, essentially, okay? And what you see on the diagonal, it's kind of a histogram of the numerical variable price, okay? It doesn't look like a histogram because histogram is like a bar chart, right? It's more stylized, more smooth, so it's a density plot, that's what it's called, okay? So it's a little bit more detailed than a histogram. Okay? So this is how prices are distributed. You can see that we have a bunch of prices in the lower range, right? And as we get into the high range of prices, there are less and less cars, right? Okay. So same thing here, okay? Age versus age, that's how cars are distributed by age, right? We have a bunch of cars which are older, right? High age. And as the age is getting smaller, we have less and less of these cars, right? So it's kind of a distribution of the variable, okay? And same thing here, right? So what's that? Mileage, right? Mostly cars are distributed in the low mileage area. Oh, I wouldn't necessarily call it low mileage, but kind of lower mileage, right? And then we have kind of tail going into the positive direction, okay? Alright. And I eliminated, oh, I didn't include fuel type, right? Should we include fuel type? Let's include fuel type, right? Because it's still in the model, right? I just wanted you to see what fuel type looks like. So I'm going to add fuel underscore type and rerun this command. So it will get one more column and one more record, right? Bam. Okay, fuel type though is a categorical variable, true? There is, yeah, it is, right? There is a compressed natural gas, or how it's called, yeah, liquefied natural gas. There is diesel, and there is regular gas, right? So you can see that this is distribution. It's pretty much counts of cars, right? So what's the most popular type of fuel in our sample? Gas, right? Overwhelmingly, many cars that use gas. What's the second one? Diesel, right? And then CNG, compressed, or whatever it is, right? Natural gas is like literally a blimp on the radar, right? So not a lot of these cars, okay? All right. So what else can we see? Off diagonal, all right? Off diagonal, what we have basically is if the two variables are both numerical, then it's a scatter plot. Let's take a look at this one, for example, okay? It's the price, right? It's in the column for price, and it's in the row for age, right? So you can see that as the age goes up, what happens to the price? The price goes down, right? And that makes sense, okay? The car is getting older, the price is getting smaller, right? And in the corresponding cell, right here, I have a correlation coefficient, okay? So it looks like age, so this is age, right? This is price, and this is column age, right? So corresponding to this scatter plot, I have the correlation coefficient of negative 0.868, right? So according to our classification of different coefficients of correlation, is it weak, moderate, or strong? Strong. Is it a good thing? Why not? Well, they're not independent, but hey, one of them is price, right? And price is my dependent variable. Do I want correlation with dependent and independent to be strong or weak? These ones I want strong, right? Yeah. So anything that deals with price, right? I want my predictors to be strongly correlated with price, right? I don't want them to be strongly correlated with each other. So let's take a look. My predictors are numerical predictors, that is, right? Age, mileage, and the horsepower. Agree? So let's take a look at this one, for example. This is correlation of mileage and age, right? So it's in the column mileage, and it's in the row for age. Correlation is 0.55. How is that? Moderate. Is that criminal? No, it's okay. Then I have, what else? Horsepower with age, negative 0.176. How is that? Weak. Is weak good? Yeah, because they're both predictors, right? None of them is my target. I'm looking only at predictors, right? Predictor 1, predictor 2, okay? So horsepower with age is weakly correlated, which is great. Horsepower with, what's the next one? Mileage, minus 0.34. Moderate, right? Is that good? Yeah, it's good. Both predictors, not strongly correlated. How about weight? Weight with age, minus 0.5. Moderate, which is okay, right? Weight with mileage, minus 0.07. Really weak, which is good, right? And that makes sense, right? Weight versus mileage. I mean, what do you expect? The more you drive, the more you lose of the car, so it gets like what, feet or something, loses fat? No, that doesn't work, right? The car is still, it doesn't matter how much you drive it, the weight's still the same, right? And that's why you don't see any correlation, so that makes sense. So, and also weight with horsepower, 0.08, which is a good thing, right? Okay, so do I have multicollinearity condition in this problem? Again, multicollinearity happens when your predictors, numerical predictors, are strongly correlated with each other. Not necessarily all of them. If you have predictor 1 and predictor 2 and they're strongly correlated, that may be by itself already a problem, right? Do we have any of this? No. None of my predictors are strongly correlated with each other, which means that I do not have multicollinearity, which is a good thing. That means that my independent variables are truly independent from each other, and I don't really suffer from any issues on that end as well, okay? So, what I wanted to point out is this. Check for multicollinearity only applies to multiple regression, okay? Why? Because if I have simple regression, that means that I have only one predictor, right? There is nothing else to correlate. There is only one x. I need at least another x to even test for multicollinearity, right? So simple regression, we never checked for this, for exactly that reason, okay? There is nothing else, basically. There was only mileage and nothing else, okay? Now I have mileage, age, horsepower, and weight. All of them are numerical, so I have to cross-correlate them with each other, okay? And that way, I will see if there are any strongly correlated variables among my predictors or not, okay? Now, how much time do we have? 6 minutes, okay. Well, what I was going to show you was basically what happens if you do have multicollinearity, but we'll probably leave it off until Friday. Let me just give you a preview, okay? House prices, okay? Let's kind of chit-chat about that. When you buy the house, what do you think is the strongest factor that determines if the house is going to be highly, moderately, or low price? In other words, what are the things that affect house price? Square footage, how big is the house? What else? Neighborhood, in other words, location, right? So here in Williamsburg, Kingsmill is going to be expensive, right? Downtown Newport News, not so much. Has it been renovated, right? So does it require like any fixing, right? Yeah. What do you mean by that? Lot, right? Lot, yeah. Land is worth something, right? So lot size, Age, how old is the house, right? Okay. New house is probably worth more than the older houses, right? Number of bedrooms, is that a factor? 3 versus 5 versus whatever, right? Yeah, so if it comes with like stove and microwave and fridge, right? Yep. Number of bathrooms, right? Yep. Versus slab, right? Foundation, crawl space versus slab. If there is a basement or not. How many stories does that affect? Yep, possibly. Material, right? So vinyl siding versus the brick house, right? That kind of stuff. Yep. So there are a lot of variables that affect the house price, right? So next class, here's what we're going to do. I have posted the file that contains a bunch of houses with their prices. And for each house, we know also square footage, how big is the house. Then Dylan said the acreage, right? How many, what's the size of the plot of land, and how many bedrooms we have in each house. And what we're going to do first thing on Friday is we'll try to build the model that predicts the house price based on other 3 things, right? House size, lot size, and number of bedrooms, okay? And then we'll see what happens, okay? By the way, who can use this model? Why is it even important? Retailers, right? So every time when you buy the house, you have to order the appraisal, right? What do you think is the current market value of the house? And appraisers, there are, generally speaking, 2 ways how they do it. the probably most popular is something that's called comparables, right? They're looking in your neighborhood in the last 6 months, and they're saying, these are the houses that were sold. Now, they're not exactly like this one, but adjusted for number of bedrooms and lot size and all that. This is what believe is the price currently for this one, right? Another way is for square footage, right? So they say, this house has 2,500 square feet. The average price for square foot in this neighborhood is, I don't know, $75. So this is what we estimate to be the price of this house. So that could be actually a very useful model for real estate agents, for appraisal agents, and people, linked with real estate in general, right? Okay, so this is it for today, and then we'll finish this example on Friday, and we'll start a new topic, okay?